Hello everyone, welcome to KINETICS. Today we are speaking with Dr. Vinay Bhandari, ANRF Prime Minister Professor at Maharaja Sayajirao University of Baroda, whose work spans chemical engineering, waste water treatment technologies, industrial sustainability, and translational research. For a long time, industrial growth and environmental sustainability were framed as competing priorities. But today, sustainability is increasingly becoming central to industrial strategy itself, shaping manufacturing systems, resource efficiency, regulatory frameworks, and technological innovation. In this episode, we'll explore how engineering, water systems, industrial processes, and sustainability transitions are evolving together in India's emerging industrial landscape. Thank you for coming, sir.
Thank you very much.
So, to begin with, Dr. Bhandari, for decades, industrial growth and environmental sustainability were treated as opposing priorities. From the perspective of chemical engineering, what fundamentally changed?
This is true to some extent, but then we need to differentiate the Indian scenario from the global scenario because we typically have 40% of our wastewater problems because of the small scale industries, and this is where we are quite different in adopting different kind of technologies to different sectors, chemical sectors. And here the question of economic sustainability and environmental sustainability, because these two things are little different in a sense that if you want to use the term sustainability, in what context you are going to use it. Environmental sustainability is of course certain goal and has to be there in today's context, but then economic sustainability was our first priority in earlier terms. When we devised this plan or adopted this particular model, we focused more on the development of small scale industries, in cottage industries, in blessing industries in rural area for giving employment and things like that. But then chemical industries, if you see, the profitability increases with the scale of operation. And if you have small scale of operation, obviously you will have difficulties in terms of skilled manpower, in terms of limited infrastructure. There won't be any research and development kind of activity in that scale, and then obviously they will have difficulty in even adopting or assimilating the technological innovations that come in the different times. So in that sense we will have problems. Secondly, when we talk about environmental sustainability, the chemical sector requires a specific kind of location, and we have difficulty in planning our townships. And then when people move close, population is close to the chemicals industry, then it is also question of their safety. For example, Dombili, you can see the population is now almost in the industry sector.
True.
So that can create problems pertaining to safety also. Forget about sustainability. It is certainly not sustainable in terms of environmental sustainability. So both these terminologies are linked with each other, and in India we have this specific problem of planning. So we need to focus more on different aspects, right, from which industry should come where, how it should come, where the population density should be there, what should be the distance, transport, all those things, facilities, infrastructure, all those things we need to focus on, and then consider the sustainability. In chemical engineering sense, we always talk about techno-economically feasible solution, because technically solution may be available for whatever, for achieving the environmental sustainability, but whether that solution is economical, that is the main concern. For example, take the case of green hydrogen. You have different colors for hydrogen, isn't it? So getting green hydrogen is not economically sustainable at this point of time. Of course, research and development will be there, and then in future some solution will be there. So all those things. So techno-economic feasibility is most important. Our industry normally focuses mostly on profitability, and maximize profit is our industry's motto. So for maximizing profit, if you have these technical solutions for environmental sustainability, for example, say air pollution control, wastewater treatment, and things like that, that typically they consider it eating into their profits. So reduce profits. So obviously their inclination towards using those solutions is not there. So this is where we have a problem in terms of the environment sustainability and economic sustainability. But technically, I don't think there is any issue. We have solutions for solving these issues.
Yeah, so I totally agree that there are so many problems, especially the urban planning, and there is a scope of improvement in the same across India. So, are we now entering an era where sustainability must be embedded directly into industrial process design rather than added later as compliance?
Certainly, but then again, changing mindset is important. Our industry typically adopts end of pipe treatment. So there is a problem and they want to solve that problem. For example, take any chemical reaction per se, and you have certain set of reactants, catalysts, solvents, etc. They and what are the impurities that are going to be there in the wastewater treatment for wastewater treatment, that also we know. So if I have to do end of pipe treatment, then obviously I can have a treatment facility to take care of those pollutants. But then if I change any parameter in the process or any raw material in the process, my the effluent treatment problem is altered altogether, and I need a separate setup or modification in the existing setup. So this is a very important when we talk about the environmental sustainability imbibed in this particular thing, no?
Hmm.
So in recent times, the concept of sustainability, um when we say for industry purpose, we talk in terms of again color,
Hmm.
that green processes, green materials. So anything like um, green process is not polluting or environmentally sustainable kind of process. So these kind of developments are there, but then right now not all chemical process can be modified as green processes. For example, in wastewater treatment, not all processes are green processes, treatment processes. There are secondary waste generating processes and things like that. So we need to focus on this in terms of research and development. But then obviously, as you said, it should be a part of the sustainability should be a core of our
Hmm.
industry.
Yeah. So your work has focused extensively on hydrodynamic cavitation technology for wastewater treatment and industrial applications. For those unfamiliar with this field, what makes hydrodynamic cavitation particularly relevant in today's industrial and environmental landscape?
At the outset, I'm little tempted to term our technology developmental work as a green process. So that can differentiate our technology from other technologies. Now, why I say this? Because if you say the conventional processing in terms of say coagulation, adsorption, all these processes have the secondary waste generation. So you are just transferring problem from one part to another part. Okay. Whereas hydrodynamic cavitation is one process where we oxidize. It is an advanced oxidation process. We oxidize the organic moiety, and the end product, desired end product, is carbon dioxide and water.
Hmm.
So we eliminate the problem altogether. So this is where the hydrodynamic cavitation is very important. Now let me little bit explain this particular thing more, because hydrodynamic cavitation is not so commonly used and not taught in our curriculum. So that's why advanced oxidation people know because of the processes like penton oxidation, other oxidation processes, photocatalysis, and all those things are oxidation processes. But what is the different thing with hydrodynamic cavitation is that we have developed in this particular hydrodynamic cavitation process our own device, which we call as vortex diode. It employs a vortex flow. Okay, and this vortex is very powerful, and at one point the pressure drop is such that liquid, some part of liquid flashes into vapor and generates cavities. Okay, these cavities travel, we allow them to travel to certain extent, grow and then collapse. This collapse is, we call it implosion, which is opposite of explosion. So it generates huge energy. At the point of implosion, it can generate temperatures of the order of 10,000 degree Kelvin and pressures of the order of 1000 atmosphere. So at the point of implosion, because of these extreme conditions, the water splits homolytically, generating oxidizing radicals, hydroxyl radicals, which oxidizes the organic moiety. And we expect that it oxidizes to a certain extent where water and carbon dioxide are the products. So this is a very simple, and our device is a very simple mechanical device without any moving elements. So this is another difference with our device, our invention. We obviously have patents, many patents on this particular technology and this particular device. So this particular device performs the job without the addition of external chemicals or harmful chemicals. It doesn't require catalyst. It doesn't require maintenance, and then operation is very simple. Pressure drop is very less compared to other devices, and that's why obviously when we say pressure drop is less and pressures are less, it is translating into the lower costs because energy cost is lower, and that's why it is more advantage, and then it has a higher efficiency for the oxidation compared to other processes. So in all these things, hydrodynamic cavitation is very good. And recently we have developed another new cavitation device which we call dual activity cavitation reactor. So this employs a very new concept of combining the catalytic activity within the reactor itself. So we surface coat this particular reactor, inner surface, and then it is coated with the metal which has a catalytic property. So typically copper, nickel, they have the silver, they have the capacity to catalyze the reaction. And then cavitation is a physicochemical reaction which is the conventional device they perform. So with cavitation and catalysis, the performance gets enhanced order of magnitude, and then the obviously efficiency for degradation of organic moiety gets enhanced drastically. So this is a very real new development. I think in 2022, 21, 22 we came up with this idea, and then we demonstrated it with different pollutants. So different sectors we can say where the molecules can get degraded, and lot of work needs to be done on this particular development now. And recently we also uh, developed technology for drinking water treatment. This is as far as wastewater treatment is concerned. Okay, so we are now oxidizing organic pollutants and then removing them, eliminating them. So in cavitation, again to have more differentiation, in cavitation, how is it different? For wastewater treatment, we have typically two type of approaches. One is removal, physical removal approach, other is a destructive approach. Okay, and most of the technologies are removal technologies. For example, coagulation. Coagulation, you remove the organic pollutants and then there is a sludge which gets generated, which is another secondary waste generation. Either you dump it or you do something with it, treat it. Okay, that is a coagulation thing. Adsorption also, you are transferring your problem to adsorbent material and then you require to regenerate adsorbent material. That again creates a secondary waste stream, and then that has to be treated separately. So these are kind of technologies, we call it removal technologies, and there are our technology is a destructive technology. So it destroys the species. So you don't have the problems and cost associated with the secondary waste generation. And recently we developed this technology or use this technology for drinking water treatment, which is another prominent area. Okay, and so far there were no reports to successfully disinfect water using cavitation technology. There were of course reports, but then not to complete disinfection. And you know, in water, unless you do complete disinfection, it is not safe for drinking.
Yes.
So our achievement is that with this dual activity cavitation reactors, where we have the conventional cavitation as well as the catalytic cavitation, and then with this we completely disinfect water, destroy all kind of bacteria, gram positive, gram negative, E. coli, S. aureus, and then also antimicrobial resistant bacteria. Many of these bacteria don't get removed or eliminated by the conventional practice of chlorination or any such thing. So that is the reason why we say that this particular technology or application of this particular technology in drinking water treatment is very useful and can really change the scenario. In fact, for wastewater treatment, when we talk in terms of engineering terms, technology readiness level is 9. So it is in the scale of 1 to 10. Typically 1 to 3 is laboratory level studies. So we have TRL of 9 for wastewater treatment technology. So it is already commercialized. Now it is in the market, people are using it. And then for drinking water treatment, the TRL level is of the order of say 4 to 6, because it is yet to be seen for commercial application. Of course, we have now started we are taking efforts in commercializing this particular technology, but then it is highly promising because the cost is comparable to that of chlorination. So it can ideally it should be possible to replace the conventional chlorination. So hydrodynamic cavitation technology actually has many, what you can say, different applications. People think more of wastewater treatment, hydrodynamic cavitation, but we also use hydrodynamic cavitation for desulfurization of fuels. This is just a totally different angle. See how fuel now sulfur removal is required, mandatory. And for fuel cell application, sulfur is required to be less than 1 ppm. Okay, so that kind of removal, and here we used altogether different concept. For generating hydrogen radical, I need water. Fuel is organic. How do I get hydrogen radical for whatever sulfur removal or desulfurization purpose? So we decided to use some water and then completed the job of desulfurization. This is altogether a very new concept, and in fact I am happy to say that we received award from Honorary Vice President for this desulfurization work. So, but then it is applicable only to refineries, only petroleum refineries where desulfurization of fuels is required, and hopefully someday they will use it. But I found one website, Chinese website, where they have my pilot plant and hydrodynamic cavitation work for desulfurization. But then Indian industries need to consider this.
Yes.
Okay.
So, in fact, our audience also got an overview about hydrodynamic cavitation technology, and thank you so much for throwing light on that. So, many sustainability technologies show strong promise in labs, but scaling them into real industrial environments is often much more difficult. So, in your experience, what are the biggest barriers between scientific innovation and scalable implementations?
So I have advantage of speaking from both sides, industry side as well as academic side, because I have worked in industry for 2 years before doing PhD. So our industry mindset is little different. Again, it comes to changing mindset. So our industry has a mindset of buying technologies ready-made off the shelf. Okay, so always they go abroad and get imported technologies for different problems or in their products. But then they also should think of developing research and development, and then develop technologies, indigenous technologies, and if not possible within their setup or their capacity, they can take help of our universities or research laboratories. They can approach the scientists working in that area and give them funding and get their problem solved. So that real life connection is there, real life implementation is there, and industry academia connect is also there. Okay, but then this is not happening right now. The simplest part, they can fund the PhD student, very simple, and then obviously they can give problem also of their choice. So this is one aspect as far as industry is concerned. And in fact, in my career, I have been part of many academia and industry meets. So there were efforts to connect this, but so far not much success in this regard, unfortunate. Now coming to the academic side, what happens? The academic culture is to explore scientific part of a particular thing, and then so more into science, more for publications, because the evaluation system is such that you will get evaluated on the basis of number of publications you have or the kind of journals you publish and things like that. They don't consider whether you have industry problems or any real life solutions or not, most of the time. So that's why people will be in their comfort zone, what I can say, and then they will have their PhD students and doing routine work. Most of the time nowadays they don't even think of coming out with new ideas also. So, for example, if you take field of nanomaterials, so synthesis of some particular nanomaterial in some particular way, characterization, XRD, same time, and things like that, routine thing. Obviously, you get data and you get the degree.
Yeah.
So it should be avoided. So, in fact, I have been suggesting in different platforms this particular thing, that we should have some industry academia connect in some particular form. Nowadays it is only happening in conferences, and that too for limited time, whereas it should be actually happening uh, over significant amount of time. So ideally, simple way, they can fund the PhD student or master student and solve their problem. And then with the interaction with the scientist concerned, obviously there will be deliberation on the different things, what is required for society, real life application, and then the scientist will be encouraged to work on those such things. And the funding is very important.
Yes.
Why our academia is more happy with working on these typical problems, routine problems, because of the funding issues.
Yeah.
That our industry universities are not funded well, and that's why there is always funds crunch. And then you have to select subjects which will have easy output also, and at the same time not much new thinking in that involved.
Yeah.
Because new thinking will always have risk associated with it. It may not work, and that failure to digest that failure is not easy in our kind of evaluation system. So that capacity also we need to generate, so that scientists are encouraged to work on new problems.
Yeah. So, in fact, PKC, Pune Knowledge Cluster, is also acting as an enabler between academia, industry, entrepreneurship, civil societies. So, we are glad to be a part of PKC. Uh, India today faces simultaneous pressures of industrial growth, water scarcity, and environmental stress. How should industries begin rethinking water, not as a disposable industrial input, but as a continuously recoverable resource within industrial systems?
Well, there is no doubt that we should have the industrial wastewater treatment, recycling, and reuse. It is imperative that we have this kind of system for each and everything. Okay, but then this problem needs different angles. Like for example, what kind of wastewater is there? So one should first think whether it is possible to recover materials. So recovery of what you can say useful materials is another one thing. Whether wastewater can be used for generating energy, that also another part. For example, when BOD is which high, you have biogas generated, and then there are different configurations, process integration, biodigesters, and all those things. So integration of that. So recovery of valuable things requires research in separation processes, because all these things will have costs associated with those things. Okay, the solutions are not cheap, and then you require materials, new materials, which will have capacity to sort of recover these materials, pollutants. These are pollutants, no, basically. So recover the pollutants economically. So we need to have smart materials, I would say, and you should also have the detection mechanism, which materials are good, which are not. So selectivity is important. So all these things will have different dimensions, in the sense that you will have to work on separations, you will have to work on other processes like biological processes, chemical processes, process integration. All those things are important. So what I should continuous resource wastewater, there is a concept, of course, of using wastewater as a resource, but it is not always possible. Depends on the composition of the wastewater. Now, of course, many people are thinking of recycling sewage wastewater, particularly because it is not what you can say very high loading or high pollutant wastewater. So there it is possible to employ the normal solutions, but then I would emphasize need for more research and development in this regard. Especially in Indian context, we require lot of efforts for recycling, and there is a huge potential. For example, in city areas you can have large volumes of sewage wastewater generation, and then you can use it in different formats, not necessarily
Yeah.
for these household purposes.
Yeah. So there's a growing discussion around circular industrial systems, zero liquid discharge, and decentralized treatment infrastructure. So, do you see these approaches becoming mainstream over the next decade, or are there still major technological, economic, or operational constraints that need to be addressed?
Zero liquid discharge is already mandated in some industry sectors,
Hmm.
like for pharma industry sector, no?
Hmm.
Zero liquid discharge, because see, API pollutant concentration is very small, but
Hmm.
then it is what you can say, very high adverse effect on environment and also human health. Hmm. So I remember long time back there was one professor giving presentation and he showed one slide
Hmm.
that one patient goes to doctor and obviously tells him that some problem, etc., and doctor takes wastewater in glass and gives him, offers him,
Hmm.
that
Okay.
you take this and you will be all right.
Hmm.
The meaning or the point that was to be conveyed was that the water contains so many pharma, so you can say active pollutant, these pharma ingredients, that
Hmm.
unknowingly you are taking, whereas the
Hmm.
doctor is knowingly giving you as a
Okay.
solution to your problem. And it happens
Yeah.
really, the levels of API pollutants
Uh,
in wastewater is huge.
yeah.
Hmm.
Um,
And unknowingly you are taking medicinal things, and then we are finding that people are now getting drug resistant,
hmm.
isn't it?
Hmm.
So that is one thing. So zero liquid discharge is certainly required, but not all industry sectors will have this kind of rigid framework. Not necessary to have this rigid. This is my
Hmm.
opinion. Pharma industry sector certainly it will be required, and there will be sectors where zero liquid discharge can be practiced, and it is possible also. Of course, it will be associated with the cost. So circular economy concept is very good, but then practicality of the circular economy and using that approach here in this particular case, where people are reluctant to do even the wastewater treatment. So
Hmm.
that's why that problem of river pollution and all those things remain. So
Hmm.
we regularly find our Indrani river polluted, and many rivers, of course, practically all rivers people say are polluted.
Hmm.
So why this problem is there? Because people are
Hmm.
releasing wastewaters
Yeah.
without treating, and it is a known thing. In my book, we have mentioned that hardly 66% of the wastewater gets treated.
Hmm.
So rest of the wastewater is simply released without treatment, and this is a problem with the Indian what you can say scenario, and we need to take care of that. So zero liquid discharge is a important concept, but not
Hmm.
applicable to all sectors.
Okay. So India has ambitious sustainability and climate goals.
And
With
then in this regard, no, I will
huh,
say, see, circular economy and what you can say distributed structure
huh,
infrastructure, no. So in India we have chemical zones
hmm,
where we have placed typical chemical industries particularly, and then we also provided common effluent treatment plants,
hmm,
CETPs, okay,
hmm,
to facilitate treatment of wastewaters. Now water should be treated as a resource, as a raw material. For example, in industry typically the water costs something like 25 rupees per meter cube,
hmm,
and for sending suppose some industry doesn't have the capacity to treat wastewater, and then they are sending it to CETPs, that also costs. So typically that cost is little more than 15 rupees per meter cube, depending on the obviously the composition of the wastewater and the
yeah,
nature of pollutants. So
hmm,
if you treat wastewater economically, you can save on the fresh water, which is
hmm,
25 rupees per meter cube. So you already have availability due to the treated water. So these kind of things are required, and some of these things are available, but then uh, they should work. So most of
hmm,
the facilities are made available, but then not in operation. That is
yeah,
another problem. Sometimes electricity is not there, sometimes manpower is not there, sometimes some other thing is not there,
hmm,
for whatever reasons. But then there are operational difficulties in this regard. So those needs also to be solved to implement the
yes,
solution.
true, true, that's true. So, like I said, India has ambitious sustainability and climate goals, and implementation often remains uneven in all the sectors. So, where do you currently see the largest gap between policy, ambition, and industrial execution?
Water management.
Mm-hmm.
Water management is one thing where we need to focus more. See, for example, India requires something like 10% in terms of domestic consumption, 10% for industry use, and the remaining 80% for agriculture purpose. So when we have water scarcity, we focus more on industries, because domestic can't be avoided. So we
Mm-hmm.
focus on industries. In fact, in summer where water becomes a problem, water scarcity forces industry to close their operation in some
Mm-hmm.
places. So those kind of situation. But how much water can be made available because of this? Sometimes constructions get closed. So you need to have parametric sensitivity analysis for taking care of this particular problem of water scarcity, water distribution, and that's where water management is very important.
Yes.
For example, if you can reduce the water consumption for agricultural sector, it can practically solve our problem of water
Mm-hmm.
scarcity. And in developed countries, the consumption for agricultural sector is very less,
Mm-hmm.
hardly 30%, 40% of that order.
Mm-hmm.
Okay, so I think we need to have this. Policymakers should have this understanding in terms of water management. Why we are spending more water for agricultural sector? Because we are having water intensive crops
Mm-hmm.
like sugarcane, rice, so all those things. So we need to really think about what should be the pattern of our agricultural thing, agricultural
Yeah.
produce.
I would like to ask you one more question. Do you think water pricing model would work in cities
Like
if we have a price for certain amount of water which we consume daily? So if we do that, will that work? There should be a limit to extend uh, use of water
I
in
think
household.
I think it may not work to the desired level,
Hmm.
because see there are certain demands which are inelastic. We call the elastic demand and inelastic demand.
Hmm.
Okay, like fuel. No matter what fuel prices goes up, people still continue using fuel. Of course, dramatically if you increase, that is a different thing, but then
Hmm.
that is a different scenario. But then water demand is something inelastic. You will
Hmm.
require water in any case.
Hmm.
I think in cities we already are paying for water. No, it is not
Yeah,
metered. Only thing. Only
metered,
thing, it is not
yes.
metered. But then I don't know. Some different experts can throw
Okay,
more,
yeah.
shed more light into this area. But in my thinking, it's not a very useful solution.
Okay,
Uh,
yeah. So, at the uh, same time, industries are increasingly adopting AI-driven monitoring systems, automation, and smart manufacturing tech. So, how do you see this process engineering and environmental engineering evolving over the next decade as digital systems become more and more integrated into industrial operations?
very true. Actually, AIML can change, transform the existing scenario drastically.
Hmm.
They can be employed for wastewater treatment, operations, detection, quality monitoring, and decision making also. So to enhance the operational efficiencies, and they can probably perform much better than what is the present system. So
Yes.
AIML will transform the existing scenario drastically. That's what I
Hmm.
expect, and for good.
Hmm.
Nothing wrong,
Yeah.
nothing bad about it. Okay,
Yes.
integration of technologies is one prime area, because wastewater treatment, what happens, no one particular technology is sufficient
Hmm.
enough to treat entirely the wastewater thing.
Hmm.
So you require combination of different technologies, and AI can help in having most effective combination in this regard, depending
Hmm.
on the water quality. So you require sensors and data for all these things as a feed. So data is
Yeah.
very important, and certainly it will be useful.
So, as you worked across academia, industrial collaborations, and research ecosystems, So, in your view, what distinguishes innovation ecosystems that successfully convert scientific research into deployable industrial solutions?
Hmm. This is one interesting question. But then, see, you tell me how many technological solutions have
Hmm.
come from academic institutions or our research
Hmm.
institutions? Not many,
Yes.
at least not in India.
Hmm.
Um, in terms of number, there will be, but then in terms of what you can say impact,
Hmm.
there are not many. We are still
Hmm.
dependent on other things. So, innovation requires teamwork and technology innovation, not innovation and technology development requires teamwork.
Hmm.
Okay, and then that is a major problem with our systems. People are happy working in isolation.
Hmm.
We absolutely have no problem in terms of number of very good people, intelligent people,
Yep.
innovating people, but then they remain in their comfort zone and tend to sort of react in the form of publications, etc., and not in terms of technology development. And technology development also requires industry support, because see, in the lab, when you are trying to develop certain thing, you require to understand the exact nature of the problem, which
Hmm.
industry can tell you, because lab is not an industry.
Hmm.
So industry can tell you exactly what problem is there, and then the person can innovate and develop technology with industry's help. So that collaboration is very important. So we
Hmm.
require people generating new ideas,
Yes.
people working on those ideas, and people consuming or taking those ideas to market.
Hmm.
So all these things are very important.
Yeah. Collaboration is definitely
Collaboration is
important
important.
because people working in silos won't make that much impact as much as a collaborating
Correct.
organizations can do. So finally, uh, if we were to look back at this decade 10 years from now, which technological, institutional, or policy decisions will matter most in determining whether India succeeds in building a truly sustainable industrial future?
Hmm. This is again policy makers' decision, but
Hmm.
then governments are required to sort of exploit the enormous opportunities in this area, particularly environmental pollution control and wastewater treatment, because it affects not just industry but society in general. So government should focus more on these. Of course, there are job opportunities. Technology
Hmm.
development will create jobs, and then implementation part. All those things will have human resource requirement and infrastructural requirements, etc. So this has not happened in the past. That is for sure. And then uh, we require government support for R&D
Hmm.
in terms of funding.
Hmm.
We do not get sufficient funding, especially for generating new ideas. People submit typically proposals, research proposals on the known ideas.
Hmm.
Hmm. And then the work, what we can say, plan is also more on the similarly known practice.
Hmm.
So methodology, research methodology is also more or less reported kind of thing. So what you generate is only data.
Hmm.
So government should provide incentive for generating ideas and
Hmm.
create what you can say um, hub for translating those ideas.
Hmm.
Because that is also very important, because scientist has to take it to outside world, that idea. So government funding is one important area. Then education is
Yeah.
another important area. I think the mindset needs to be changed, and that should happen right from primary education. It
Hmm.
doesn't happen altogether in the last end. Um,
True.
so that is so education sector government should fund well.
Yes.
Teachers don't get paid well, so
Hmm.
which is also not good, a good sign. See, because they are transferring knowledge from one end to other end, like
Hmm.
teachers are transferring to student.
Hmm.
So that is very important. So for that you require good teachers, good infrastructure in universities, laboratories, and access to those infrastructure, basically instruments, etc. Not many people many times, many universities, obviously the potential is there, teachers are good, researchers are good, students are also good, but then they lack the facilities to pursue their research program, and obviously that limits their research and output also. So those things are required. This has not happened previously, and obviously it is a policy kind of thing, decision, and the improvement should come first from government, and obviously the universities have a lot of job to do, recruit good people. I would say give importance to merit.
Mm.
Merit is the most important criteria, should be the most important criteria in this regard, whether it is in terms of employing the teachers, whether the selecting or scrutiny, the screening of the proposals, research proposals, funding. Give importance and priority to only merit. So merit-based education is the need of the hour.
Yes. So, Dr. Bhandari, thank you very much for walking us through these important questions around industrial sustainability, water systems, process engineering, and the future of environmental resilient industrial infrastructure. So, for our audience, if you would like to stay engaged with these conversations, you can follow PKC, where we continue exploring issues at the intersection of science, tech, sustainability, and industrial transformation. Thank you, Dr. Vandari, once again, and thank you all for watching the episode of Kinetics.
Thank you very much. And then in conclusion, I would say one thing, that what is most important in Indian context is changing mindset. We require honesty, professional ethics, and then integrity, most importantly. And that will change the entire scenario, whether it is environmental pollution control or in any other field. So these are the three ingredients that we need to sort of have it in our system, right from education to all other sectors. So thank you very much once again for
Thank
giving me
you.
this opportunity, and thank you all.
Thank you.